Right guys, welcome to the next video, and this time we're going to be looking at empirical formula and stoichiometric ratios and equations. You don't need to know the ins and outs and the theories of this, but what you do need to know is how to determine an empirical formula and how to determine a molecular formula from empirical formula. So that's what I'm going to take you through today. Obviously you can read this information here, I just don't want to read it to you, but you might be asked this for definitions and to explain yourself, so you do need to know it. The first steps that we're going to look at is what is empirical formula, and it is the simplest ratio of atoms present in a compound. So for example, we have butane here. You'll learn a lot more about butane later on, but what we do know is it's got 4 carbons, 1, 2, 3, and 4, and then it's got 10 hydrogens because we double it and we add 2. There is a simple way of showing this, which is C4H10, and that tells us how many carbons and hydrogens are present in that molecule. And for sometimes really large molecules, not necessarily butane, but the ratio, so the empirical formula, can tell us more information about that thing. So the empirical formula for this would be C2H5. If you look at this number here, all we've done is halved it. We can't half it any further because then we'll have H2.5, and that's not a whole number, and that doesn't exist. What I'm going to ask you guys to do is, for this task here, can you find the simplest ratio of these things? I can take you through the first one just to have an idea of what I'm looking for. So, the simplest number of ratio for this molecule right here. An easy trick for you guys to do is to just keep halving it until you can no longer half it and get a whole number. Let's start with that first of all. So 6 halved is going to be 3. Got H10, which is going to be 5. And then Cl2, which is just going to be 1, so I'm just going to leave this bit here. Can I do it again? Not quite, so then I have C1.5, H2.5, and then Cl0.5. And you can tell that already looks a mess, and it's just wrong. What I'd like to do is have a go at answering the next series of questions. Okay. What we're going to do is we're going to step up the difficulty this time, and now we're going to look at finding the molecular formula if you've been given the mass. So sometimes they might say there's a molecule that has this type of empirical formula. We know it's got a ratio of 432 carbon, hydrogen, oxygen, and we know that the mass of it is 166. So can you tell me what this thing might be? And there's quite a few simple steps for this, and I've broken it down into these 3 here. The first one we're going to do is we're going to find the empirical mass. I'm going to do some highlighting so you can see where I'm looking, so you know what I'm talking about. So step 1, find the empirical mass. In order for us to do that, we need to find the mass of the ratio. So the empirical mass is the mass of the ratio. We're going to need a periodic table, so if you go to the back of your booklet, you should have a periodic table there. And you'll see I've got 4 carbons, so 4 times 12, add 3, because it's 3 times 1, and then add 16 times 2, because we've got 2 oxygens. When you get all these numbers together, we get 83. So you can see that that's where that number's come from. We're then going to divide the molecular mass by the empirical mass. I'm going to highlight this so you can see these numbers here. So the molecular mass we've been told, so the relative molecular mass is 166. And we're going to divide that by our empirical mass. So this and this. This is going to give us a value known as empirical units. They don't really exist. It's just kind of a way to determine the ratio. So it's what we're going to call empirical units. So we've got 2 of these. Finally, you're then going to multiply the ratio, so your empirical formula, by those empirical units. You'll see on my page that there is actually a typo, but in your booklets it shouldn't be there. But what we're going to do, so you zoom in, we're doing the empirical units, which I've done in green. I'm going to multiply that by the molecular, so the empirical formula, and then we're going to get a final molecular formula, just like that. And when I say multiply by 2, what I'm saying is this value, this one, and this one. So it'd just be 8, 6, and 4, just as I've got here. That's really straightforward, but I do want you guys to actually have a practice of this. And just so you don't forget the steps and having to go backwards and forwards, what I've done for you here in the video is I've given you a step-by-step instruction for the first 2. And then for the third one, I would like you to have a go at that by yourself. For the first one, though, I do want to help you out and take you through it. So let's go through that one step by step. And then for the second one, you guys have a go. And then third, it's on you. So the empirical formula for glucose is CH2O. So that's the ratio of it. Its relative molecular mass is 180. So the first thing we need to do is find the empirical mass. So we're going to find the mass of CH2O. 1 carbon, 2 hydrogens, 1 oxygen. Add them together. If you're working along with me, you'll have got the answer of 30. And if you're just sat there putting me on 2 times speed, you'll have also got 30, but you wouldn't have had the practice. please have a go at doing this yourself. Even if you can see it on the screen and you know how to do it, it's really important that you do it yourself, because if you make a mistake, at least you make the mistake now. The next step is to do empirical units. So for those of you that are practicing along with me, I would like you to have a go at calculating the empirical units if the relative molecular mass is 180. You should get an answer of 6. And then what we're going to do is going to multiply that molecular formula by the empirical units. So everything in this ratio by 6. Again, have a go. And you should have got an answer like this. And this is how I presented it. For the next step, I'm not going to take you through this one, but you can use the steps above to help guide you. And then for the third one, a little bit more tricky, and you can see over here, I've got Cl2 and O, and you're going to need a periodic table to get the relative molecular mass, or the atomic mass of chlorine. I'd pause the video here, have a go at this, and then I'm going to take you through a next step, which is a little bit more difficult as well. Okay. The final form of looking at empirical data is to determine the empirical formula using experimental data. This can present itself in two different ways. You might see it in grams. So they might say, oh, we've got 17,000 grams of this. Or they might say, we have X amount of percentage of carbon, X amount of percentage of hydrogen, and Y amount of oxygen, or something like that. And from those values, you can actually determine the empirical formula, and you can determine ultimately the molecular formula as well. It's really good in, obviously, experimental chemistry, but also analytical chemistry, where you might have a couple of substances that you're not quite sure what they are, but using this method, you can actually analyze what the substance is, and you can get a final answer. And we can use that in forensics. Let me take you through the first step. I'm not trying to hide the answer. It's in your booklet, so you can see it right in front of you, but I blocked it out so you can see the step-by-step when I talk you through it. So the question reads, calculate the empirical formula of the compound formed when 5.4 grams of aluminium reacts with 4.8 grams of oxygen. So you can see already you might be thinking, let's use a balanced equation, but when you see the term empirical formula, this gives you a different process. What we need to determine first of all is the ratio of the masses. So the way we're going to do that is I'm going to highlight it for you so you can see where I'm looking. We're going to use the 5.4 grams of the aluminium, and we're going to use the 4.8 grams of oxygen. Now, aluminium on the periodic table is 27, so you can find that for yourself. And the mass of oxygen is 16. So we're going to divide them by that. So it's the experimental value you've been given divided by its molecular mass, or atomic mass in that case. Once you put that into a calculator, you're going to then get an answer of 0.2 and 0.3. That's going to be the final one there for you. Now we've got this ratio, we need to do something with it. This is where it gets a bit confusing for some of you. So what we're going to do is we're going to divide it by the lowest one. So you've got your ratio. Now, which is the lowest of those ratios? It's the 0.2. Divide everything there by 0.2. And it should look a little bit like this. This is now going to give you some whole numbers that you can actually work with. So you're going to have the 1. And you should see here, you're going to have 1.5. So this is going to give us the value. So I know that I now have a ratio of aluminium 1 and oxygen 1.5. Now, I said earlier that we can't have 1.5 oxygen. It doesn't exist. So what can we do? The easiest way to do this is we're just going to double it until we get whole numbers. In some instances, you might have to multiply by 3, but in this case, we can just double it, and we're going to get that 1.1 to 1.5. It's a 2 to 3 ratio, and therefore we're going to get aluminium 2 and oxygen 3, so Al2O3, which is aluminium oxide. There are a lot of steps to follow, so what I'd like you to do is follow along and go with me through this one using my step-by-step breakdown. So what we've got first of all is we've been given percentage data this time, and in that percentage data, we've now been given a molecular mass. So what we're going to be using is that percentage data instead of the mass like we did before, but we're still going to do it the same way. Just like before, I'd like you to follow along with me. So the first step, we're going to divide the percentages we've been given by the mass of carbon, mass of hydrogen, and mass of nitrogen. Again, I wait along for you, but I think it's just better if you pause the video and then we can double check if you've got that process right. And you should have an answer here that looks a little bit like this. So you should have this. Again, I would write this process out because if you skip steps, you at least know where you went wrong. Again, you should get this in your calculator. Now, we're not working with nice clean numbers like before. We've got these weird decimals going on, and that's okay. We can still work with that. What's the lowest of these values? We've got the ratio. We now need to get the lowest, and it's a 2.2. So we're going to do 4.6 over 2.2, then the 15, then the 2.2 over 2.2. And it should look like this. When you put this in a calculator, you're then going to get close to whole numbers. And what I've done is I've rounded them up. So you'll see they're really, really close. And I get 2, then 7, then 1. Which means finally, I have C2, H7, N1. Which I'm going to write just like this. And then that is your empirical formula. Notice, at no point did we use that 45. But if you want to double check your answers correct, so if I want to check this is correct, what we can do is we can then work it out from there. Or if it doesn't add up, we can use this and this to determine the molecular formula using the step we used above. You find the empirical mass, you find the empirical units, you use the molecular mass and then the molecular units to get the final answer. So we can do that as well. The next step, I'm going to give you guys a little bit more freedom. I want you guys to have a go at this. I have tried to highlight it just to make it a little bit more clearer of what you're doing. And I give you some tips on the side, but you can use the answer from above to help you out. All right, enjoy. The very, very last part is stoichiometry. Again, there's not really much to teach you here other than the fact that we're just trying to balance things. So essentially, if we're going to make a sandwich, we're going to need 2 pieces of bread and a slice of cheese. So we need 2 bread, 1 cheese to make 1 sandwich. That's all stoichiometry is. It's making sure that you have the right amount of things to make the right amount of products. And what I've got here for you is some very weirdly worded questions that should help you think about it. So what I've done is I've changed some of the numbers here for this example right above. And what I'd like to do is to use those sentences to make sure you can get the correct ratio of the things that you might need. To give you an example of what this reaction is looking for, is I've got 4 lots of sodium, so 4 moles of sodium. It's going to react with 1 mole of oxygen, and every time I do that, I make 2 lots of sodium oxide. If I doubled this and doubled this, how much of this would I make? Yeah, you're right, I would make double the amount. If I halved this, half the product, how much of these things would I need? Yeah, half the amount. So I could just half this and we can get the same amount. So that's essentially the method that I'd like to use for this, is have a look at the numbers and try and work it out. It's a bit more of a puzzle than anything, but in the meantime, I'll leave you to it. Enjoy.